Chapter 14 Acids and Bases. Acids and bases are important substances in health, industry, and the environment. One of the most common characteristics of acids is their sour taste. Lemons and grapefruits are sour because they contain organic acids such as citric and ascorbic acid. Vinegar tastes sour because it contains acetic acid. We produce lactic acid in our muscles when we exercise. Acid from bacteria turns milk sour in the production of yogurt and cottage cheese. We have hydrochloric acid in our stomachs that helps us digest food. Sometimes we take antacids, which are bases, such as sodium bicarbonate or milk with magnesia, to neutralize the effects of too much stomach acid. Acids and bases have many uses in the chemical industry. Sulfuric acid is the world's most widely produced chemical. It's used to produce fertilizers and plastics, to manufacture detergents, to conduct electricity and lead-acid storage batteries for automobiles. The base sodium hydroxide is used in the production of pulp and paper, in the manufacture of soaps, in the textile industry, and in the manufacture of glass. In the environment, the acidity or pH of rain, water, and soil have significant effects. When rain becomes too acidic, it can dissolve marble statues and accelerate the corrosion of metals. In lakes and ponds, the acidity of water can affect the ability of plants and fish to survive. The acidity of soil around the plants affects their growth. If the soil pH is too acidic or too basic, the roots of a plant cannot take up some nutrients. Most plants thrive in soil with a nearly neutral pH, although certain plants, such as orchids, camellias, and blueberries, require a more acidic soil. The pH of a solution describes its acidity. The lungs and the kidneys are the primary organs that regulate the pH of body fluids, including blood and urine. Major changes in the pH of the body fluids can severely affect biological activities within the cells. Buffers are present to prevent large fluctuations in pH. Section 14.1 Acids and Bases. The term acid comes from the Latin word acidus, which means sour. We're familiar with the sour taste of vinegar and lemons and our common acids in foods. In 1887, the Swedish chemist Svante Arrhenius was the first to describe acids as substances that produce hydrogen ions when they dissolve in water. For example, hydrogen chloride ionizes in water to give hydrogen ions and chloride ions. It's the hydrogen ions that give acids a sour taste and change the blue litmus paper indicator to red and corrode some metals. Naming acids. Acids dissolve in water to produce hydrogen ions, along with a negative ion that may be simple nonmetal ion or a polyatomic ion. When an acid dissolves in water to produce a hydrogen ion and a simple nonmetal anion, the prefix hydro is used before the name of the nonmetal, and its "ide" ending is changed to "ic" acid. For example, hydrogen chloride dissolves in water to form HCl aqueous, which is named hydrochloric acid. An exception is hydrogen cyanide, which is an acid named hydrocyanic acid. When the anion is an oxygen-containing polyatomic ion, the "ate" in the name of the polyatomic ion is replaced by "ic" acid. If the acid contains a polyatomic ion with an "ite" ending, its name is "us" acid. The halogens in group 7A can form more than two oxygen-containing acids. For chlorine, the common form is chloric acid, HClO3, which contains the chlorate polyatomic ion. For the acid that contains one more oxygen atom than the common form, the prefix "per" is used. HClO4 is named perchloric acid. When the polyatomic ion in the acid has one oxygen atom less than the common form, the suffix "us" is used. Thus, HClO2 is named chlorous acid, and it contains the chlorite ion ClO2 negative. The prefix "hypo" is used for the acid and has two common oxygen atoms less than the common form. HClO is named hypochlorous acid. The names of some common acids and their anions are listed in Table 14.1. HCl, hydrochloric acid. HBr, hydrobromic acid. HCN, hydrocyanic acid. HNO3, nitric acid. HNO2, nitrous acid. H2SO4, sulfuric acid. H2SO3, sulfurous acid. H2CO3, carbonic acid. H3PO4, phosphoric acid. HClO4, perchloric acid. HClO3, chloric acid. HClO2, chlorous acid. HClO hypochlorous acid, and HC2H3O2, acetic acid. Bases. You may be familiar with some household bases such as antacids, drain openers, and oven cleaners. According to the Arrhenius theory, bases are ionic compounds that dissociate into cations and hydroxide ions when they dissolve in water. They are another example of a strong electrolyte. For example, sodium hydroxide is an Arrhenius base that dissociates completely in water to give sodium ions and hydroxide ions. Most Arrhenius bases are metals from group 1 and 2A, such as sodium hydroxide, potassium hydroxide, lithium hydroxide, and calcium hydroxide. The hydroxide ions give Arrhenius bases common characteristics, such as a bitter taste and a slippery feel. A base turns litmus paper blue and phenolphthalein indicator pink. Table 14.3 compares some characteristics of acids and bases. Arrhenius acids produce hydrogen protons. Arrhenius bases produce hydroxide ions. They are both electrolytes. Acids taste sour and bases taste bitter. Acids sting. Bases are soapy or slippery. Acids turn litmus red and bases turn litmus blue. Acids are colorless in phenolphthalein indicator and pink when it's a base. And an acid neutralizes a base, and a base neutralizes an acid. Naming bases. Typical Arrhenius bases are named as hydroxide. Sodium hydroxide, potassium hydroxide, calcium hydroxide, aluminum hydroxide.